Let's look at isotopes. Now, isotopes are elements that have the same number of protons and electrons but have a varied number of neutrons. You need to know the definition. Now, let's look at the characteristics of isotopes. Because they have the same number of electrons means that they will have the same electronic configuration. And the same electronic configuration means that they will have the same chemical properties. So chemical properties depend on electronic configuration. And if they are the same, they will have same chemical properties, which means that they will react in the same way. Also have different physical properties that include boiling point, melting point, and conductivity. Now, when we look at periodic tables, we see the big numbers at the bottom. These show the relative atomic mass of each element, and these are decimal numbers. We get these from a mass spectrometer, which produces a mass spectrum, and a mass spectrum gives us these data. A mass spectrum looks like this. So you are going to have peaks, and then you're going to have percentage associated to these peaks. So each peak in the mass spectrum represent a particular species. So let's see how it works. You don't need to know the functioning of a mass spectrometer, but this is just for you to know what happens in it. So we're going to have a sample which is going to be injected in the spectrometer. It's going to be vaporized, so we're going to have gas. So you have the sample which turns into gas, and then the gas is going to become ions. So we're going to ionize the sample, so it's going to turn into ions, and then the ions, we're going to have positive ions generated. So we have electrons that hits them, so you have electron that goes out, so we end up with positive ions, and then the positive ions are going to be deflected by a magnetic field. Now, depending on the mass of the ions, of these positive ions, they are going to be deflected by different amounts. The heaviest species is going to be deflected the least, and the lightest species is going to be deflected the most. When these positive particles hit the detector, they generate an electric signal, and these electric signal, this is what appears as the peaks. And we end up with a mass spectrum. So in a mass spectrum, you're going to have peaks. The number of peaks will indicate the number of isotopes. The position of each peak indicates the relative isotopic mass. So the isotopic mass is the mass of that particular isotope. For example, when I'm saying I have chlorine 35 and chlorine 37. 35 is the isotopic mass of this isotope. 37 is the isotopic mass of this particular isotope. So the position of the peaks, so here you have 35, it's for this particular isotope. So this is the mass of that particular isotope. If I could say the AR of that particular isotope, and this one is the AR of that particular isotope, all right? And the height of the peaks correspond to the relative abundance of these isotopes. So the height here, this is going to tell us how much of chlorine 35 we have, and here it tells us how much of chlorine 37 we have. So from this information, from this mass spectrum, we can see that there are two isotopes. One of the isotope has relative isotopic mass of 35. One of them has relative isotopic mass of 37. And then they also have their corresponding abundance. So these are the three information that we can get from the mass spectrum. Now, to generate comparison for all atoms, chemists use the most abundant isotope of carbon, which is carbon-12 here. And carbon-12 has 6 protons, 6 neutrons, and 6 electrons. Now, you've come across the definition of relative atomic mass in IGCSE. So, if you still remember, relative atomic mass is the mass of an atom of an element compared to 1/12 the mass of a carbon-12 atom. So carbon-12 is taken as the anchor or as the reference element to be able to attribute a relative mass to all other elements. We're not working with actual masses, we're working with relative masses. Now, why do we use carbon-12 out of all other elements? Long ago, different scientists in various parts of the world use different elements as the relative elements. Some used oxygen-16, while others used a mixture of the different isotopes of oxygen. But what happened is that their results were not comparable, and each one was not able to use the results that the other scientists got. So there was lack of uniformity across the sciences. So then we agreed on one other element. So we decided to use carbon-12 because carbon, even if it has other isotopes of carbon, the majority of the isotope is carbon-12, right? Now, to bring down the mass to 1, so we say 1/12 the mass of carbon-12, right? So it's widely available and it's a reference for all the scientists so that their results can be compared to each other. So the term relative atomic mass, so it is the weighted average of masses of the isotopes of the elements. So for example, chlorine exists as chlorine 35 and chlorine 37. So the AR of chlorine would be the weighted average. Weighted average means the percentage of chlorine 35 taken into consideration, so 75% of this, and then the average of this, so 25% of this. These two, the weighted average, and then the average of this, so 25% of this. These two, the weighted average, when you calculate it, it gives you 35.5. So the AR is the weighted average of the isotopes relative to 1/12 the mass of a carbon-12 atom, right? So carbon-12, so 1/12 the mass of a carbon-12 atom, that brings down to 1, right?